The focus of lesson 3 is what we call the discrete time Fourier analysis, right? And the discrete time Fourier analysis is related to Fourier analysis, right? But since we are actually dealing with discretized time signals or discretized one-dimensional signals, so we're going to call it discrete time Fourier analysis. And because of this discretization process, we actually have to be quite careful about the sampling of those continuous time signals, actually. And there's some additional complications that's introduced by this discretization process, and we have to sort of pay special attention to, right? And so that will be the focus of lesson 3. And now let's look at lesson 2. Probably the most important result from lesson 2. It's in lesson 2, we are basically representing any kind of signal, an arbitrary signal, using a building block. That building block is called a impulse sequence. Basically, we can express any kind of signal as a linear superposition of those shifted and scaled and shifted impulse sequences. And if we use this kind of a representation for an arbitrary signal, then the output signal of any linear time invariant system can actually be expressed using what we call a convolution operation. And this convolution operation is basically this expression, right? So if you actually use h, this particular function, this particular signal, as to denote the impulse response, the response of the linear time invariant system, if you actually put a impulse as its input, right? H is going to be the output, and this output is called impulse response. And then the output, if you actually use x as the input to that linear time invariant system, here denoted as L, right? And then the output is going to be a weighted superposition of those shifted impulse responses, right? If you actually compare this formula with this formula, you sort of see the kind of similarity, right? Both of them are linear superpositions, right? And the input is a weighted summation of shifted impulses, right? And the weights are given by xk, the amplitude of the input signal, right? And then the output yn can be expressed as the same kind of linear superposition of shifted impulse responses, h, right? And the weights are actually identical to the weights that's used here, right? And this particular expression, this particular summation, is expressed using a star, basically a convolution operation, right? That's what we call the convolution. And that's probably the most important result that we have reached in lesson 2. And of course, we also talked about lots of other stuff, right? We also talked about correlation, convolution and correlation, their relations, right? Their differences, right? And then different kinds of basic signals, basic operations applied on those basic signals, and lots of stuff, right? When we talked about those different kinds of basic signals in lesson 2, it's not just the impulse sequence, right? We also talked about another kind of building block, another kind of basic signal or basis signal. That's the complex exponentials, right? Complex exponentials is also a very widely used basis signal, and we can actually represent any kind of a signal, an arbitrary signal, using this kind of a building block also, right? This kind of representation is actually not unique, right? If you are using basis functions that's shifted, or basis signals that's shifted impulse sequences, then you have this kind of expression, right? But what's going to be the expression if you actually use this kind of basis as your basis signal, right? So how can you actually represent this arbitrary signal as linear superpositions of complex exponentials, right? But before we actually do this kind of a representation, or do this kind of a decomposition of an arbitrary signal into complex exponentials, let's try to understand why people try to use complex exponentials as a basis signal, right? What's actually the benefit for using this kind of signal as a basis signal, right? The benefit of using a delta sequence or shifted impulse sequence as a basis signal is kind of obvious, right? Because of this convolution, right? It gives you a way for representing not just the input signal but also computing the output signal by using this convolution operation, right? And then what's the benefit? What's the benefit of using complex exponentials, right, as the basis signal? So let's go back to analyze the convolution operation, right? Let's try to take another look at the convolution operation, right? In lesson 2, we basically expressed convolution. We basically wrote a computer program to implement this convolution operation by calling the Matlab function that's called COMV, right? And inside of the COMV, it's basically implementing this summation over k. It's basically just implementing this summation over k and this multiplication, right? And also shifting. But there's another way for implementing convolution, and the Matlab actually gives you several functions for you to actually do that. You can implement the convolution as a matrix vector multiplication. So basically, you can use linear algebra operations to implement the convolution, right? And the way for doing that, is actually quite convenient. It involves a particular function that's called conv mtx. So if you haven't used it before, you can sort of type help conv mtx. It's called convolution matrix, basically. It's called convolution matrix. So it's telling you that conv mtx convolution matrix, it allows you, it's going to return the convolution matrix for vector c. If c is a column vector and x is a column vector of length n, then conv mtx cn times x is the same as conv cx, you see, right? So conv mtx cx times x equals to conv cx, right? Suppose x is your input signal, and this vector c, this column vector c, is actually your impulse response, right? And then conv cx, convolution cx, actually means the convolution between your impulse response and the input signal, right? And Matlab is actually basically telling you that if you actually use the output of conv mtx cn to multiply with the input signal x, you're going to get the same result, right? So it's basically telling you the convolution operation can be expressed using matrix vector multiplication because x is a vector, right? And then the output of this particular function is a matrix, right? And it's something that's called a convolution matrix. It's a special kind of a matrix, right? So let's look at an example. Let's look at an example how we can actually construct a convolution matrix, right? And let's assume that h equals to, that's our assumed impulse response, 1, 2, 3. Let me just use space, 1, 2, 3, 4, 5, just 5 points. But let's transpose it, because if you actually just write it like that, it's going to be a row vector, right? And then this prime is going to transpose a row vector, so you get a column vector, because conv mtx actually takes a column vector, right? Takes a column vector, right? So let's try to, and then let's try to generate a arbitrary input signal. Let's just use Gaussian normalized random sequence, 7 rows, 1 column. Again, we are generating a column vector for x for the input signal, right? So here I'm not sort of particularly careful about what's going to be the horizontal axis for both signals, right? We can assign some horizontal axis to them, but for this particular exercise, that's not particularly important. But let's look at what's going to be the output of conv mtx, right? The convolution matrix. So here the first input is going to be the impulse response h, right? Now it's a column vector, And then what's going to be the second? What's going to be the second input? Second input here, it shows that it's big N, right? What's supposed to be the big N? And x is a column vector of length n. So big N is supposed to be the length of the other signal that you're actually multiplying with, right? Multiplying the matrix with, right? So it's supposed to be the length of x. Let's print out the content of big matrix A, right? So let's just run this thing and see what A actually looks like. So now it's displaying A. It's displaying A. So here's a. So if you actually look at the structure of A, what does it actually tell you, right? What does it actually tell you? So how many rows do you have if you look at the size of A? It's got 11 rows and then 7 columns, right? So for the 7 columns, you can sort of look at its content. H goes from 1 to 5, right? The amplitude of H goes from 1 to 5. So for the first column, you sort of see 1 to 5, right? And then for the second column, 1 to 5. So it's basically just a repeating H. It's basically just a repeating H for all the columns, right? And every time it repeats H, it shifts the row number by 1 downward. You see. So by the last column, which is this column, 1, 2, 3, 4, 5, the last element in the H actually reaches the bottom of the matrix. You see, right? So that's how you actually look at the columns, right? How you actually look at the columns. But if you're actually doing a linear algebra multiplication of A with respect to X, if you do a matrix vector multiplication, do A multiply X, right? A multiply X is a column vector that goes here. The multiplication goes this way. So it's the first row times the column of X, right? Every element, do an element-wise multiplication and then do a summation, right? That's basically the rule of linear algebra, right? So you are basically multiplying this row with all the elements, do an element-wise multiplication with all the elements inside of the column X, right? And that's for the first row, first column of the output vector, right? And then if you look at this one, that's if you multiply this row with the column vector X, then it's gonna give you, and then element-wise multiplication and do a summation, then it's gonna give you the second row's first column of the output vector, right? So if you actually pay attention to how the rows are ordered, you're gonna see something that's kind of strange, right? It's kind of a little bit strange, right? So here it's actually complete 1, 2, 3, 4, 5, right? And then here it's another complete 1, 2, 3, 4, 5. It's just shifted, right? But it's actually time reversed, flipped. It's actually the H signal as a row vector. If you actually look at H as a row vector, then it's basically a flipped H that's being shifted, right? Here it's actually being shifted to the first element, right? To 1, and then you shift it by one position, right? You increase the amount of shift. So basically the rows of A is just a shifted, flipped impulse response, right? And then if you actually go back to look at this particular summation, linear algebra matrix vector multiplication actually involves a summation, right? So what I claim is that the summation that's involved in this A multiply X is actually the summation here. Exactly the same, actually. It's actually a summation over K. Right? And this H, n subtract K, is actually represented by this A matrix. So if you actually look at the H as a function of K, not as a function of n, as we actually have talked about in lesson 2, right? It is indeed a flipped H and then shifted by n, right? So if you look at the H as a function of K, then it's a flipped or folded H, and it's shifted by n, factor of n. And then you can sort of see the correspondence between this particular function and all the different rows of A, right? The different rows of A are indeed flipped or folded H, right? Because it's reversed, right? And then it's also shifted, right? Different amounts of shift. Do you see? But if you shift too much, some of the elements in the H is going to disappear, go out of range, right? Right. That's for the first row, and also for the last row, right? For the last row, you have just the one element, non-zero elements, right? And all the rest of the elements are becoming zero, right? Because you have shifted the signal too much, right? So the non-zero numbers in H has gone out of range, and then the front is sort of filled with zero, right? So if you can actually see the correspondence between this particular summation, this formula, and the matrix vector multiplication, let me just finish the code. A times x, right? A times x. Let's just call it y equals to this, right? And then I'm gonna do a y1 equals to COMV hx, right? And then I'm gonna do a plot. Hold on, and then do a stem of y, right? And then use black, and then do a stem y1, use color red, for example, right? So if y actually equals to y1 is sort of doing the convolution using the Matlab COMV function, right? But y is actually computed by multiplying the convolution matrix with x, right? If they are identical, then you should not see any black signals. And they are indeed identical, right? You don't see any black signals here. Do you see? So this basically is a kind of a validation of what I claim. What I claim is that convolution can be expressed using matrix vector multiplication, right? Using matrix vector multiplication. So if you can actually do linear algebra in a very efficient way, doing this kind of matrix vector multiplication in a very efficient way, then this becomes a quite efficient method for computing convolution, well, computing the output of a linear time invariant system, right? And that's sort of the I'll show you the connection. I'll show you the connection of this kind of representation of convolution with Fourier analysis in the following, discrete time Fourier analysis in the following. So once we can actually represent convolution as a matrix vector multiplication, then we can use lots of things that we have developed in linear algebra to study convolution operations, right? And the most useful concept is what we call the eigenvector or eigenvalue, eigenvector and eigenvalue, right? So what exactly is an eigenvector of a matrix, right? So if you do a linear algebra multiplication, matrix times vector, right? A times x, matrix vector multiplication. If you can actually represent this matrix vector multiplication using a scalar vector multiplication, then lambda is called the eigenvalue and x is called the eigenvector of A. And this kind of eigenvector is kind of very nice because essentially you actually have converted a matrix vector multiplication with a scalar vector multiplication, right? It actually involves a lot less calculations, right? A lot fewer calculations, right? Because the matrix vector multiplication is kind of expensive. You have to do lots of multiplications and summations, that kind of thing. A scalar vector multiplication is a lot cheaper, right? You just multiply scalar element-wise to every element inside of the X, right? And the eigenvector is this kind of vector that provides this kind of very nice property, right? So if you are actually multiplying matrix A with a vector X, and then the result can be expressed using a scalar lambda times X, the same vector X, then lambda is called the eigenvalue and X is called the eigenvector, right? So X is an eigenvector of A and lambda is an eigenvalue of corresponding to X. So and this kind of eigenvector this kind of eigenvector is not sort of arbitrary. If you actually just use an arbitrary vector, you probably won't get this kind of property, right? For any kind of for given matrix A, right? And this lambda also depends upon the particular matrix A and also the corresponding eigenvector X, right? This lambda is also not arbitrary, right? And in fact, you can actually solve this particular equation, right? Suppose you have a, right, and then you're trying to solve for lambda by using this particular equation, right? You can actually come up with a linear algebra equation. That's how you actually determine the eigenvalues of a matrix A, right? By solving this particular equation, right? With lambda as the unknown variable, and then you can sort of, in order to for the solution to be sort of unique, right? You have to make sure that the determinant of A subtract lambda is like a 0 or something, right? That's the way that you evaluate eigenvalues and eigenvectors. So eigenvalues and eigenvectors are kind of special vectors and special values, right? And they have this kind of one-to-one correspondence, right? Sometimes eigenvalues can repeat, right? You can have multiple eigenvalues that has exactly the same value, right? Sometimes, right? Depending upon the structure of the matrix A. So an eigenvector is a very nice vector. It allows you to convert matrix vector multiplications into scalar vector multiplications. It's a very nice vector. And then what I claim is that this complex exponential, if we are actually using a complex exponential as an input to a linear time invariant system whose impulse response is h, right? And then this particular complex exponential is actually an eigenvector of the convolution matrix that we used to represent the linear time invariant system, right? So here it's the impulse response, and here's the convolution, right? And in my previous slide, I was telling you that this convolution operation, can be expressed using matrix vector multiplication, right? And that matrix is actually given here, but it can be constructed from H by using this Matlab function called CONV MTX convolution matrix, right? So essentially, you are actually taking this as the input, this complex exponential as the input, right? You are replacing x. You're replacing x with this particular complex exponential, right? So now let's bring this particular input into the convolution formula, right? A summation over k, hk e to the j omega 0 and subtract k. If you compare this particular formula with the formula that I was using in the previous slide, which is what? So here's the convolution, right? But the input signal has a k, and then the impulse response is n subtract k, right? Indexed using n subtract k. But it's okay. Here, if you compare it with the input signal, I was actually folding and shifting the input signal. It's for the independent variable of the input signal is n subtract k, but hk, right? H is k, right? Looks like it's inconsistent, right? But it's okay. It's okay. The reason it's okay is because it's because convolution operation is commutable. So in the end of the lesson 2, I was telling you that convolution has some very nice properties, right? Association, commutation, right? Commutation. So you can sort of do this, use this n subtract k either on h or on x. It's okay. It's gonna give you exactly the same result actually. So here I'm actually using this n subtract k to index into the input signal x and k to index into h, and then the summation over k, right? What I can tell you is that this kind of a formula is actually consistent with this formula because of the commutation property of convolution. So and then this summation is over k, right? It's a summation over k. What's depend upon k? H depends upon k. And then e to the j omega 0, and then j omega 0 has to times n subtract k, right? But at least the j omega 0 times n does not depend upon k, right? So this is j omega 0 times n is a factor that we can actually take out of the summation, So if you take this thing out of the summation, what you get is e to the j omega 0 n, and then the stuff in the square bracket all depends upon k, right? So it's hk times e to the minus j omega 0 k. Do you see the operation here? It's there's some algebraic manipulations, right? But it's not really that difficult. So here I'm actually just extracting e to the j omega 0 n outside of the summation k, right? And then the square bracket, the stuff that's inside of the square bracket is sort of depends upon k, and it's a summation over k, right? It's a summation over k. Right? And if you this summation over k is actually a number. It's a complex number, but it's still a number. It's a scalar, right? Because you have summed over all the k, and omega 0 is some number that you have selected, right? It's some arbitrary real number that you have selected, omega 0, right? Right. And this summation over k will actually, after this summation is done, then there's no dependence on k anymore. So the whole thing that's inside of the square bracket is going to give you a number, right? A scalar. And we can denote this particular scalar using this particular symbol, h e to the j omega 0, right? Because it's a number, right? And the result of this number, this summation, depends upon omega 0, the value of omega 0 that you have picked, right? You can pick any kind of omega 0. E is a constant. The j is sort of the imaginary unit, right? You don't really have to care about e and j. But omega 0 is something that you have picked, right? It's something that you have selected. It doesn't really matter what value you select, right? So as long as you selected a value, then this is actually just a number. Could be a complex number, but nevertheless it's a scalar, right? So if you actually compare this expression with this expression, do you see the consistency? E to the j omega 0 n, e to the j omega 0 n, right? So what I was telling you is that I was using e to the j omega 0 n as the input signal, so you can treat it as a column vector, even though each element in that column vector could be a complex number, right? But still, it's a vector. It's a vector of x column vector, right? And then this convolution can be represented using a convolution matrix, right? So essentially, this is a times x, and here it's still x, right? E to the j omega 0 n is still x is a column vector, and then this is a scalar, right? It's just a number, could be a complex number, right? And then if you compare this side with the left-hand side of this equation, right-hand side of this equation, it's exactly lambda times x, right? So what this analysis is actually telling you that e to the j omega 0 n doesn't matter what omega 0 actually is. It's an eigenvector of the convolution matrix. And the corresponding eigenvalue, lambda, is actually given by this particular value. And this particular value has a formula for computing it. It's this thing. It's basically a summation of k over k, a summation over k. And then hk is basically the impulse response times e to the minus j omega 0 k. Right? There's a minus sign here, so you have to pay attention to this minus sign. It's kind of important, right? It's kind of important. So basically, this slide is just telling you that e to the j omega 0 n is an eigenvector of any kind of linear time invariant system, and the corresponding eigenvalue is given by this particular summation over k. Right. Now, if we can actually express any kind of input xn as a linear superposition of complex exponentials, still with the summation over k, right? We represent it as a linear superposition of e to the j omega kn. You see, so here it's not just omega 0, one value. It's a lots of values, lots of omega k. I'll tell you how to select those omega k, right? But nevertheless, xn is expressed as a linear superposition or weighted summation of complex exponentials with different omega k, right? and the weights are given by AK. Right? So suppose we can come up with this kind of a representation of an arbitrary signal, right? And e to the j omega kn becomes the building block, the basis signal, and the AK becomes the coefficient. Then what's going to be the output for a linear time invariant system that has an impulse response of Hn, right? It becomes really simple, right? Because you can just take this expression and then take it and stick this expression into this convolution, right? Convolution, and then what you are gonna get is a linear superposition of AK times e to the j omega times this particular number, and then times the eigenvector, right? Because I know that e to the j omega kn is an eigenvector. It's an eigenvector, right? And then if I actually convolve it with Hn, which is equivalent to do a matrix vector multiplication, right? Do a matrix vector multiplication, then the result is going to be H e to the j omega k, big H e to the j omega k, times the eigenvector itself, right? The eigenvector itself is e to the j omega kn here, e to the j omega kn here, right? So the whole thing is going to be the response. This thing that's under the selection is going to be the response of the system to this particular eigenvector, right? And then all I have to do is to multiply another scalar AK here, and then do the same summation over K, the same summation over K, right? So basically, the part here is unchanged. The part here is unchanged. All I have done is all I have to do is to multiply this eigenvector with its corresponding eigenvalue. You see, this big H is its corresponding eigenvalue, corresponding to e to the j omega kn, right? And this eigenvalue is what? This eigenvalue can be computed by doing this particular summation, and it's computable. You can compute it. You can compute this summation, right, for every omega k. For every omega k that you are using for representing this arbitrary input signal, right? So then it comes to the next question: how do you actually compute AK, right? How do you actually obtain this kind of representation, right? How do you actually obtain this kind of representation, right? As soon as you can obtain this kind of representation, the convolution result becomes obvious, right? So how do we actually compute AK? And the procedure for computing AK is what we call the discrete time Fourier transform, or DTFT. This formula actually represents discrete Fourier transform, and if you have used the FFT routine in Matlab before, FFT actually is just a very fast implementation of the discrete time Fourier transform. It's called a fast Fourier transform, right? So it's an implementation of this particular formula, this discrete time Fourier transform formula, that's adapted to the modern implementation of digital computers, basically. So one of the reasons that Fourier transform has become so fundamental and so popular in all science and engineering disciplines is just because this particular transform, this particular equation can be implemented very efficiently on digital computers, right? And because of the emergence of digital computers or personal computers as some kind of a very popular thing. Almost everyone has a digital computer these days, so Fourier transform actually becomes a really useful tool just because you can do that very quickly using a computer. So before we talk about how this kind of a discrete time Fourier transform can be implemented, in particular using Matlab, of course we have FFT, right? But let's still try to implement it by ourselves and see how we can actually write our own codes to implement discrete time Fourier transform, right? But before we do that, let's look at two very important properties of DTFT, right? One important property is what we call the periodicity. So this function of omega, this if you actually sum over all the n, right, all the indices of the time series n, right, it becomes a function of omega only, right, because it doesn't depend upon n anymore. You have done the summation over n. It does. E is a constant, j is a imaginary unit constant, n has a so you have summed over n already. So the rest of the function is just a function of omega, right? So here I'm actually writing it as x e to the j omega. So it looks like it's a function of e to the j omega, right? But because e is actually a constant, j is also an imaginary unit, it's also a constant. It's in fact a function of omega. So what this particular formula is actually telling you is that this function of omega is actually periodic, and the fundamental period is actually 2 pi. So if you actually add 2 pi times the integer to the frequency omega, then you get the function back. So you get the original function back actually. So it has a periodicity of 2 pi, right? And the fundamental period is 2 pi basically. So if you don't see that, let's try to look at this derivation. So suppose I put, so if I add 2 pi L to omega, if I add 2 pi L to omega in this particular formula, and then the summation formula becomes what? Still a summation over n, right? N from minus infinity to positive infinity xn times e to the minus j omega plus 2 pi L, right? Omega plus 2 pi L times n, right? And then you can expand it. You can expand this particular formula. So what you end up with is xn times e to the minus j omega n. That's exactly the same as before, right? That's exactly the same here as before. But now you get another factor that's here. That's this thing. That's this thing. E to the minus j 2 pi n l. Do you see? Because n is also integer, l is also integer. N times l is still integer. So it's basically e to the minus j 2 pi times an integer. And if you still remember the Euler's formula, it allows you to convert a complex number to this kind of exponential form, and it also allows you to convert the exponential form to cosine plus I sine this thing, right? Cosine this thing, subtract here, it's because it's a minus sign, so it's a cosine 2 pi n l subtract j sine 2 pi n l, right? And cosine 2 pi n l equals to 1, and sine 2 pi n l equals to 0, right? So this whole complex exponential is actually 1. It's actually unity, right? So that gives you the old formula back. Basically, that proves that 2 pi l is basically a period of this periodic function, right? So that's why you have this periodicity. If you add integer times of 2 pi onto omega, you get the old function back, right? Periodicity. And what's actually the implication of the periodicity? It means that even though omega here is a real number, right? It can go from like minus infinity to positive infinity. You don't really have to study the whole real line for omega, because omega is periodic. The function is periodic with respect to omega, and it has a period of 2 pi. So all you have to do is to study one segment that's 2 pi long, right? All you have to do is to look at the omega in a certain interval, which is 2 pi long, right? It can go from like a minus 2 pi to positive to 0, or from minus pi to positive pi, or from 0 to 2 pi, or from minus a quarter pi to positive 3/4 pi, right? So any interval that's 2 pi long is enough, right? Because the function itself is periodic. It just repeats itself over 2 pi intervals. So you don't really need to look at any interval that's beyond like longer than 2 pi, right? You have redundant information if you actually look at an interval that's longer than 2 pi, right? That's the first property. A second property is some kind of symmetry property. Here's a star. Here's a star. I used star to represent a convolution before, but here if you actually put a star as a superscript, it actually means conjugation. So conjugation means what? Conjugation means that you just change the sign of the imaginary part and then keep the real part untouched, right? That means conjugation. So here it actually means that if you put a minus sign on omega, so if you change omega to minus omega, all you have to do is to conjugate the whole function. The effect of looking at negative frequencies is actually just looking at a conjugation of the frequencies, that's conjugation of the function at positive frequencies, right? So it means what? It means the real part of this particular function, big X, is even symmetry. It's symmetric. It's an even function of omega. So the real part of X is an even function of omega, and the imaginary part is an odd function of omega, right? And the implication is that you don't even have to look at an interval that's 2 pi long. All you have to do is to look at an interval that's pi long, because it's symmetric. So if you choose your interval from like minus pi to positive pi, right? That's too long. You can cut it in half. All you have to do is look at the interval that goes from like 0 to pi, right? Because you know from this symmetry property, you know that from minus pi to 0, you have a symmetry. The real part is identical. It's a symmetric to the positive frequency, and then the imaginary part is anti-symmetric with respect to the positive frequency part, right? And if you don't see that, if you don't see this this symmetry property right away, let's look at this formula, right? Let's look at this derivation. So here I'm putting a minus sign onto omega, right? Again, I bring up the summation formula. N goes from minus infinity to positive infinity, right? This formula here, right? But with the omega replaced with minus omega, right? Here I have actually changed omega to minus omega. So if you change omega to minus omega, you get you get this thing, right? So don't forget about the Euler's formula, right? This thing has, if we can we can replace this complex exponential with the Euler's formula, right? So it's a xn times cosine omega n. It's actually cosine minus omega n, but because the cosine function is actually an even function, so cosine minus omega n actually equals to cosine omega n, right? And then subtract j times sine minus omega n, right? Because we know that sine function is an odd function, right? The sine function is actually an odd function. So later on we can actually move this minus sign outside of the window. But let's before we do that, let's try to sort of rearrange the formula. So I can multiply xn into the square bracket, right? So xn multiply cosine omega n with the summation, right? And then subtract j, and then again xn multiply into sine minus omega n, xn sine minus omega with the summation, right? Yeah. So now let's take the minus sign out of the sine function, right? Because it's an odd function, so I have to sort of move this minus sign here. So this subtraction becomes a addition, right? It's a minus becomes a plus, right? And then you have reached the conclusion, because this particular formula is exactly the conjugation of the old formula, right? So this formula is actually exactly the conjugation of this formula, right? If you actually expand this thing using Euler's formula, expand it into like a cosine j omega n subtract j sine omega n. But here you have cosine omega n plus j sine omega n with xn sort of multiply on top of it, right? So that's exactly the conjugation, because the imaginary part has to change the sign, right? That's the conjugation. That's the definition of the conjugation. So here you get another property. That's the symmetry property. So if you change the sign of the frequency omega, you get the conjugation of the original function, right? The conjugation of the original function. So the implication is that combining these two properties together, the implication is that all we have to do is to consider omega that belongs to 0 to pi, and that's enough. We don't really need to look at any sort of frequency that's beyond pi. We don't even have to look at any frequency that's on the negative side of the axis, right? You don't have to look at negative frequencies at all. So this is quite convenient, right? Now let's look at how we can actually implement this summation formula, right? How we can actually implement the discrete time Fourier transform, or DTFT. And here's sort of a pseudocode, so the kind of algorithm that we can use to write the DTFT code, right? Suppose xn has this many samples, big N samples, that's between n1 to n2, right? And then we have to evaluate the big X e to the j omega at a sequence of omega values, right? Let's call it omega k. And because we don't really need to look at anything that's beyond pi, right? So we can limit ourselves to a sampling of the interval that goes from 0 to pi. And how do we actually sample it? We sample it evenly, right? So k goes from 0 to big M, right? And omega k equals to what? K times k divided by M times pi, right? So when k equals to 0, so it's 0 times pi over M. That's 0, right? And when k equals to big M, it's big M times pi over big M. That's pi, right? So omega k has a range that goes from 0 to pi, exactly, right? And how many points does it have? How many samples do we have? We have M plus 1 samples here, right? Because k goes from 0 to 1 to M, so it's M plus 1 samples, right? So now let's look at how we can actually implement this particular formula, right? So here it's big X e to the j omega k equals to summation L. Now L, because here I'm actually using small n to indicate the time axis, basically. N goes from n1 to nl, n big N. So I have to use another index L. L goes from basically 1 to big N, right? But in principle, it's just different values of n, different values of time, basically. But the time has an index that's called L here, and then goes from 1 to big N, right? So now what's actually the formula? The formula, we still need to sum over x and L, right? X and L. You can just think of x and L as xn. It doesn't really make a difference. L is just another index because I use the n to sort of. I use the letter n to represent some kind of number between n1 to n big N subscript again, right? And then what's going to be this complex exponential, right? If we go back to look at the old formula, it's what? It's e to the minus j times omega times n, right? But omega now, it's omega k now, right? Omega k, and n is nl, right? So what's actually omega k, right? What's omega k? Omega k is what? Pi divided by big M times k. Pi divided by big M times k. And then what's n, right? N is nl. nl, right? So that's going to be the complex exponential that we have to write, right? And what I can tell you is that this particular formula can again be implemented using matrix vector multiplication, right? So you have x, that's your input signal, right? That's your input signal. And then all you have to do is to construct this particular a matrix that's W, so that this matrix vector multiplication actually gives you this particular summation, right? And then how do we actually construct this W, right? Right? How do we the formula is actually quite simple, right? The formula is actually quite simple. It's if you examine this particular complex exponential, it has two indices, right? One is k, the other one is nl. One is k, the other one is nl, right? Pi over big M is a constant. J is a constant, right? So basically this complex exponential just depends upon k and nl. So we can make a matrix. We can make a matrix so that it's the number of rows and columns depends upon the size of k, or the range of k and nl, right? So here it's how you can actually construct this matrix. So this matrix has big N, this many rows, and then this many columns, n plus 1 columns, right? The big N is what? Big N is actually the range of NL, right? NL, because the X input signal has this many samples in time domain, right? And then n plus 1 is the number of samples in the frequency domain. It's the number of k. It's a range of k that goes from like 0 to big M. So you have n plus 1 samples, right? And then how do you actually construct this W? Again, you use some linear algebra multiplication. So N, suppose N is a row vector, right? Suppose N is a row vector. You transpose it, and then this becomes a column vector. Basically, it's a column vector times k. If you imagine k as a row vector, right? Row vector. So n transpose is a vector that has n rows and 1 column because it's a column vector. And k is what? K is a vector that has 1 row and n plus 1 columns. So if you actually do this linear algebra multiplication in Matlab, you're going to end up with a matrix, right? It's going to be a matrix that's n rows, n plus 1 columns, right? And then this is just all these are just the constant to multiply with it. And then Matlab exponential function actually applies element-wise. So it's basically the exponential of every element of this particular matrix, right? So once you have this particular matrix, all you have to do is to carry out this linear algebra multiplication using this matrix times the transpose of the input time domain signal, right? Because this gives you a column vector. So now let's look at some examples, right? Let's look at some examples how we can actually do this. So let's keep using our old script called s2.m, right? In s2.m, I already did some kind of convolution matrix stuff, right? Carrying out the convolution by using a convolution matrix and linear algebra multiplications. So here let's try to implement this DTFT algorithm, right? Let's try to implement this algorithm, and we need some vectors, some signals that we can actually use as an example. So what I'm going to do is that I'll generate a input signal. N goes from like the input time domain signal. It has a horizontal axis, goes from -1 to 3, for example, right? And then x, the amplitude of the signal goes from 1 to 5, suppose. It's just an arbitrary signal. And then that's basically my time domain signal. So n goes from -1 to 3. So how many signals? That's how many points? 5 points, right? So it's 5 points. And then I have to construct the omega axis, right? Omega k goes from pi from pi divided by big M times k. K goes from 1 to big M, right? So how many? What's going to be the size of big M, right? So let's assume big M equals to well, 500, I suppose, right? And then small k goes from 0 to big M, right? So that's small k. Small k goes from 0 to big M, and big M actually equals to 500. And then we can construct omega, right? So we don't really have to type a Greek letter omega. We can just use W to replace omega, right? So what I'm gonna do is to do pi divided by big M, right? It's pi divided by big M times k. That's it. And that's gonna be our omega axis, the frequency axis, right? And then we can compute our transform now. Transform equals to transpose of x times exponential of this particular complex matrix, right? So what's going to be the formula, right? X equals to, right? So the reason that I'm putting a transpose on x is because I was assuming small x here is a column vector, right? But if it's constructed as a row vector already, we can just use x directly, right? Don't forget this has to be a linear matrix linear algebra multiplication. It's a vector matrix linear algebra multiplication. So no dot multiply. It's just a star. And then all we have to do is to construct this particular matrix, right, inside of the square bracket. That's the exponential minus j times pi divided by big M. That's our omega, right? Dot hat the n transpose times k. I think I got right. I think that should be correct, right? Replace complex I and j by 1i for speed and improve the robustness. So instead of using j, I should use 1i. So that's Matlab's recommendation. And then we're getting our complex signal now. So let's give it a try, see if we can actually run it. It looks like it has finished running already because it's a really short sequence, right? But we need to sort of look at this particular signal. How are we going to look at this particular signal, right? This x is going to have the size of x is going to be 1 row and 501 columns, but it's going to be a complex sequence. It's a complex signal, right? And then for complex sequence, we need to sort of look at either the real part or and the imaginary part, or the magnitude and the phase angle, right? So let's try to sort of do a subplot. So 2 rows and 1 column. And then for this first subplot, I'm gonna plot the amplitude of the x signal. But before we actually plot them, let's try to compute it. Let's just call the amplitude magx equals to abs x. Right, that's basically the amplitude of it. And then let's also compute the angle of x equals to phase angle. The phase angle actually equal, you can just use the Matlab angle function. And then the real part of x, you can use the real function, and imagx equals to the imaginary part, magx, right? So that's going to be the 4 sequences that we're going to look at. So here I'm actually plotting what? What's going to be my horizontal axis, right? My horizontal axis, I can use w. That's going to be in terms of the omega, right? That's going to be in terms of the omega that goes from like 0 to pi, right? But I can also use, for example, k. That goes from like 0 to 500, right? So I'm going to normalize it. So I want my horizontal axis to go from 0 to 1. 1 actually means pi, right? 1 means pi. And what I can do is to use k divided by like big M, right? Or I can use omega or w divided by pi, right? Either way is fine. So here I'm going to use k divided by M. That's going to be my horizontal axis. And then mag x, let me put a grid. And then let me put some labels on it. X label is what? X label is a frequency in pi. And then Y label. Maybe not Y label. Let's just use the title. Magnitude. And then let's do a subplot 2 to 2. And then plot k divided by M. But this time it's gonna be the angle, right? And gx divided by pi. Not frequency in pi, but frequency in pi, right? And then the title should be the phase angle. And there's a plot 2 to 3. Plot. It's gonna be the real x. real part, and then subplot 2 to 4. And then title is imaginary part, right? Let's just give it a try and see what we are gonna get. Right, so that's gonna be our magnitude, right? Magnitude, and then that's our phase angle, and then that's the real part, and then that's the imaginary part, right? So it looks like our discrete Fourier transform, actually discrete time Fourier transform, or DTFT code actually works, right? And it's actually implemented just by using linear algebra operations inside of the Matlab, right? And we did not really write a particular function for doing that. We can write a function, and I can show you guys how to sort of encapsulate the codes here, into a function call, right? Into a function, so that we can call it easily, right? Not we don't have to sort of construct the horizontal axis, that kind of thing, or implement this particular formula, type very long formula every time, right? So this time domain signal, the signal in the time domain, let me open another figure just to show the time domain signal, right? And then stem nx. It just looks like this, right? It's not sort of particularly complicated. That goes from like minus with the amplitude that goes from 1 to 5, and then the horizontal axis goes from minus 1 to 3, right? And then this plot actually gives you the Fourier transform, or a DTFT, of this very simple looking sequence, right? And then it looks like a lot more complicated than this one, right? But there's a significant benefit for representing the signal using this particular complex sequence, right? And we have talked about the benefit of doing that. And we're going to look at more examples later on, and we're going to look at some properties of the Fourier transform, and how those properties can be useful when we try to sort of use DTFT in practice.